Hi, my name is Sayegh, and this is my semester video for my ENPM809T Autonomous Robots class with Dr. Stephen Mitchell. Over the past 4 months, I've built my robot and developed software to increase its level of autonomy. With the COVID pandemic changing everyone's lives, this semester's grand challenge had a very applicable objective. Specifically, my robot was tasked to autonomously navigate a simulated vaccine distribution facility and deliver 3 vials, one by one, from the cold storage area to the injection area. I'll get more into the specifics of my grand challenge later, but first let me talk a bit about my robot. So this is the final version of my robot. It is all controlled by this Raspberry Pi computer, which is powered by a battery pack. It has 4 DC motors, making it an all-wheel drive, giving power to each wheel independently. Here's a DC motor for one of the wheels. All of these motors are controlled by this H-bridge right here. It has 2 encoders on one of the front left wheel and one on the back right wheel. You can sort of see an encoder right here. These encoders are used to localize my robot and track distance that it travels. It has a Raspberry Pi camera right here, which is used for computer vision, specifically for detecting different objects using color masking, for QR code detection, for arrow detection, and facial detection. It has an ultrasonic distance sensor right here. This is used for avoiding collisions and approaching objects carefully. Has a servo motor, which is connected to this gripper, used to pick up objects. And finally, it has an IMU, which is controlled by an Arduino Nano. This is used to improve the turning accuracy of my robot by providing an angle at which the robot is. Here you can see the chassis, motors, and wheels before assembly, and then the motors and encoders assembled to the bottom plate. And this is the initial version of my robot. Then I added the robotic gripper to the front of my robot. Here I'm using encoder data to make a control loop for the robot to drive straight, and as well as turning. And then I added the IMU, which you can see here, which dramatically improves the turning capabilities of my robot. In this first clip, it is turning just with encoder data. Not great as it hits the batteries. This time it uses the IMU, and the turns are much more accurate as it avoids the batteries. I did not have access to a 3D printer, so I built the mock vials out of wood and bought spray paint and painted them accordingly. Here you can see my robot retrieving just one of the vials. And here it is using an arrow for localization, figuring out which way it's pointing and turning. One issue I was having was that my robot was front heavy, which caused the rear wheels to slip, especially when turning. To counter this weight balance, I decided to attach a Ziploc bag full of rice to the back of my robot. You can see here that this reduced the slippage of the rear wheels. The bag of rice is sometimes in contact with the ground and pressed up on the encoder wiring, so I modified this further by fixing chopsticks, allowing a safe place for the rice to sit on. Here you can see the final version of my robot after finding the optimal amount of rice to reduce slippage. Another upgrade I made was adding some cardboard to the mock vials to improve the success rate of picking them up. The simulated vaccine distribution facility I created was an 11 by 11 foot arena with the cold storage area in one 2 by 2 foot corner and the injection area in the opposite 2 by 2 foot corner. Starting in the cold storage area, my robot had to decode a random QR code specifying which vial to pick up, red for Pfizer, green for Moderna, and blue for J&J, and deliver that vial to the injection area using at least one arrow and another QR code for localization during navigation. Once in the cold storage area, the robot could only release the vial if a human's face was detected. Then the robot would go back to the cold storage area and wait for another QR code to deliver a new vial until all three had been delivered. I had 2 attempts during the Grand Challenge. During the first attempt, my robot struggled to decode the initial QR code, but eventually picked up the correct vial and delivered it to the injection area. Unfortunately, on the way back to the cold storage area, my robot turned into the wall and thus that attempt had ended. The second attempt went much better. Although my robot did not pick up the red and blue vials successfully, it continued on and made the trip to the injection area 3 times as it should have. This next clip will show the performance of my robot during the Grand Challenge when it successfully delivered the Moderna vial to the injection area and traveled back to the storage area. Following that will be a short time-lapse video of the same run from the robot's perspective using the onboard camera. Here is a trajectory mapping of my first attempt showing where it failed. And here is the second attempt. So that about wraps up my semester in this autonomous robots class. I had a blast in this class. It was super fun applying everything I've learned in all my other classes into an actual physical robot and kind of getting my hands messy and debugging and fixing out all the kinks that come with robotics. So yeah, thanks for watching.